We're going to start talking about mixtures of gases. And I have a question for you. Do we typically just have masses of pure gas? You're sitting in it. You're sitting in a mixture of gases. The atmosphere is a mixture of gases. It's more the exception than the rule that some sample of gas is just one pure gas. If you blow up a balloon, you are mixing gases into it because you're taking, the nitrogen and the oxygen that you've inhaled from the atmosphere, lots of carbon dioxide that you're exhaling. So we typically are dealing with mixtures of gases. Now, what we know about gases is that they have different masses. Different gases have different masses. They also, when they're in combination, and this gets beyond what we can do here, because of the fact that they have different masses, they exert different forces on their containers, which means they have different pressures. Oh. So, remember John Dalton? Dalton! Yay! It was Dalton who first hypothesized, and I think later did a pretty good job of sort of, not proving, but supporting in the lab, the idea that when you have a mixture of gases, the total pressure they're exerting on the container is just the sum of their individual pressures. So if I have this balloon with, we're going to make this simple, CO2, N2, and we'll throw in a little bit of argon. Okay? So I have 3 different gases in this balloon, and the gas in this balloon, in total, in this balloon is exerting a pressure outward on the balloon of, we'll keep it in relatively reasonable numbers, 770 torr. So this is probably somewhere near sea level. This could be here. And, the pressure outside the balloon is 770 torr, whatever our atmospheric pressure is today. So the gases inside are exerting that kind of pressure. Well, that total pressure is made up of 3 individual pressures. So this is Dalton's law of partial pressure. And if we were to write an equation for that, we would write it like this. We would just say that the total pressure is equal to the sum of the pressure of the first gas, and the pressure of the second gas, and the pressure of the third gas, and the pressure of the fourth gas. We could have 400 gases here. It doesn't matter. We could have 2 gases. Okay? It's the sum of all of those pressures. So in this case, the total pressure is equal to the pressure of the CO2 plus the pressure of the nitrogen plus the pressure of the argon. We can solve for any one of those. So if I tell you that the CO2 is exerting 400, I'll put a decimal there, 400 torr on the container, and the N2 is exerting 173 torr, oh that's way too, no, let's make that a bigger number, 227 torr on the container. What is the pressure of the argon? It keeps pausing itself. Okay, so we can solve for this by just doing P total minus the pressure of the CO2 minus the pressure of the N2 is equal to the pressure of the argon. Go ahead, do it. Okay, so I get 143 torr as the partial pressure of my argon. Why do we care about this? Where could this ever be useful? You're actually going to do a lab at the conclusion of this chapter, so I will give you the pre-lab for it Monday, and we'll do it Tuesday, because it bridges the concepts between Chapter 10 and Chapter 11. So in the lab that you're going to do, you're going to have to figure out the volume of hydrogen gas produced. And you have to account for the pressure on it, because the pressure and the temperature changes. Well, how do we measure gases that are produced in a laboratory setting anyway? We do something called collection of gases under water. Having missed all the cool, fun, exciting stuff with pneumatic troughs, now we've got this container with some water in it and some gas in it, if we find a total P, we know that that's the pressure of the water plus the pressure of whatever other gas we want. In this case, it was CO2. We find this by looking it up. It is purely a lookup. It is purely 100% a lookup. So at 20 degrees Celsius, what's the partial pressure of water? Okay, so at 20 Celsius, partial pressure of water is what, 17.0 torr, or millimeters of mercury? 17.5? Okay. Now, where do we get this total pressure number? Where does that come from? Is that glass jar exploding or contracting in on itself? Then the pressure inside the glass jar must be equal to what? The outside pressure, the atmospheric pressure. So we look it up on a barometer, and we happen to have a barometer on the wall. Today's atmospheric pressure is, we can call that 766.5. 766.5 torr is our total atmospheric pressure. So now we have two of the three pieces. We can solve for the pressure of our carbon dioxide that we produced. So P total minus P of water is going to be the pressure of our other gas. So when we do that, we get 766.5 torr minus 17.5 torr. I will post homework practice problems for this concept. They'll be up by 5C, and I'll make sure they're on PBWorks. Do some practice. Tomorrow I will be out in the afternoon, so you will have a sub. You will have time to work, and then you'll have a. We may have to do homework due Friday, test Monday, quiz Monday. So we'll do a FIP quiz on Thursday and wrap up on Friday and homework. Okay, have a good day.